Hello, everyone. Thank you for joining us for this Is Potassium the Answer to Your Crop's Nutrient Needs webinar? My name is Katherine Garcia, and I will be the moderator for the webinar. This presentation can be used for one nutrient management CCA continuing education credit using the QR code at the end of the webinar. In 1959, AgSource was formed to serve Wisconsin dairy farmers. What began as a regional dairy records processing cooperative has grown into the AgSource of today, serving industries that span the entire agricultural ecosystem. From cutting-edge soil, plant tissue, and water testing to agronomic consulting and full-service DHI testing, AgSource at its core is a source of truth. One test at a time, we help our clients make the best decisions, always grounded in data. I would now like to introduce you to our presenters. Starting us off today is going to be Dr. Jim Friedrichs. Jim holds the position of Director of Laboratory Quality and Research at AgSource Laboratory, supplying technical information to industry and agronomic consultants throughout the world. Soil and environmental science are central interests in Jim's work and educational expertise. He received his BS in agronomy from University of Kentucky and a PhD in agronomy focused in soil fertility from Virginia Tech in 1989. Also joining him today is Garrett Johns. Garrett is an agronomic support specialist at AgSource. He brings 11 years of agronomic expertise to the table. 7 of those years were dedicated to serving as a precision crop advisor for a prominent ag retailer, where he spearheaded a successful weekly tissue sampling program and corn and soybeans. Garrett's knowledge extends globally as he continues to assist industry and agronomic consultants and clients around the world. Leveraging his proficiency in agronomic testing, he earned his BS in agronomy from the University of Nebraska-Lincoln and joined the AgSource team in 2021. I'd now like to turn it over to Jim to get us started.
There we go. Welcome. Thank you. I'm Jim Friedrichs, as Kate said. I work in quality assurance for the AgSource Laboratories. And today we're going to be talking about soil potassium, a plant nutrient. Focusing on potassium because it's one of the 3 essential nutrients, and it seems to be one of the things that is often difficult to manage just because of the complexity of how it interacts with the soil. We think that maybe it's easy to apply potassium and it'll be there in the future, but if we don't understand how it is impacted by the mineralogy and the base saturation, the cation exchange capacity of the soil, there's things that affect its availability that we can actually expound on a little bit today and try to see if we can get a better handle on how those things interact. So these are the topics that we'll be looking at, looking also at content of potassium in the soil and some information about how we make recommendations and how we can use those recommendations maybe to tweak what is actually applied and how it serves the plants. Potassium is generally in good supply in the soil. This is a picture of the potassium content provided by the U.S. Geological Survey, and it shows the relative concentration of potassium across the United States. You'll notice some areas are blue. Those areas are lower than the median, meaning that the lower than average, lower than the general potassium concentration in the soil. The green tinted areas are the median ranges, and then those that trend to yellow and red are above average or above median. And this is the A horizon. This is the soil where we can impact changes in the soil potassium concentration where it's affected by plant uptake, et cetera. If you'll keep your eye, just pick a state and look at that as I go to the next slide. You'll see that not all soils are the same, because some soils have a reserve underneath in the C horizon that actually continues to supply potassium to the soil. So even down here in the southeast, where it's generally blue, that means there's lower potassium content. There are spots where there is a high potassium in the subsoil that can become available, that can be tapped by the plants if they can extend their roots down that deep. The Fertilizer Institute conducts a survey every 5 years where they collect information from all the soil testing labs across the country. And they present this in terms of pK, pH, organic matter. But this one, potassium, is particularly interested and relevant to today's topic. And if you look at these numbers, the bold numbers are those median values from their soil test data from that state. So you can see in the southeast, those median numbers are lower than the values in the Midwest or in the upper Midwest, where they're actually quite high. And that just reflects that same image that I showed in the last two slides. The number in the brackets is the target potassium level that a fertilizer recommendation is designed to achieve. And so you can see in the southeast, those targets are generally higher than the median value, meaning that most soils are deficient in potassium and need to be supplied potassium consistently in order to achieve optimum crop growth. Whereas in the Midwest, Illinois, Iowa, Ohio, and even up into Minnesota, those soils, the median values and the target values are fairly close, indicating that most of the samples, most of the soils provide enough potassium or more than enough potassium, but there are still those that need and will respond to potassium fertilizer. Then you go farther west, west of the Missouri River in Nebraska and the Dakotas, and even farther west, the median values for potassium in the soil are much higher than the sufficiency ranges or the target ranges, indicating that there are a lot of soils that will not respond to potassium fertilizer. There are some, of course, that are below median, but generally these soils are rich in potassium. The Pacific Northwest is a little bit different. There's mixture there with different kinds of soils, as you see in California, where the target levels are lower as well. To just expound on this or to develop this, I think it's important to understand why those soils supply potassium in different ways. What's different about the soils? What is important in terms of the structure? So clay is a predominant factor. So we'll look at the importance of clay, how potassium interacts with the clay, and then how that interacts with availability of K in terms of cation exchange, and maybe even some of the ways we look at cation exchange. Clay, in the textural triangle, clay is a dominant part of the texture of the soils. It's the largest fraction of this triangle, and it has a very dominant effect on the mineralogy, obviously, but the availability of nutrients, because it interacts with most of the nutrients in ways that regulate the supply as well as the retention of nutrients, and particularly the cations, of which potassium is the one of interest today. Soil clays are generally of two forms. There's a 2-to-1 type of clays, which are predominant in our temperate soils in the center part of the United States. This is also true in temperate areas of Europe and other continents, but we're focusing primarily on the US, so I'll just use these as examples. 2-to-1 type clays are derived from minerals that are rich in potassium, calcium, magnesium, and they form in these classic structures. There's a silica tetrahedra, an alumina octahedra, and then a silica tetrahedra, and that just 2-to-1 pattern repeats over and over again. If we look at that in terms of the molecular structure of the clays, you can see that the silica tetrahedra down at the bottom part where you see those triangles is the upper layer. There's triangles there, and then there's the prisms in between. Those are the alumina octahedrals. And then the silica tetrahedron is the bottom layer as well. That triplicate just repeats over and over and over again to form a clay structure. What is interesting is that these bonds, signified by the round circles, those are the oxygens or the hydroxyls, whereas the silica and the aluminum occupy the center part of each of the trapezoid or prism shapes. What can happen, though, is that alumina can substitute for a silica. And silica has a +4 charge, aluminum has a +3 charge, so you end up with a net negative charge on the surface of that arrangement, that tetrahedron. And the same happens with the aluminum, where magnesium can substitute for the aluminum, and you get a net negative charge because magnesium is +2 and aluminum is +3. These net charges will attract cations to the surfaces of these clays because the charges are internal, but they're expressed on the surface of the clay mineral. So then to graphically look at these different structures, excluding the one on the far left, the mica, the illite, the vermiculite, smectite, those three in the center are the classic 2-to-1 type structures. You have the tetrahedron, the octahedron, and the tetrahedron with something in between, which is in this case, in the case of the mica and the illite, is potassium, which is very tightly held in between the layers, and then the layer repeats, and that repeats over and over again. So you have a sandwiched layer of potassium between the 2-to-1 type structures. That's true for mica and illite. For miculite, you have that same interlayer space, but there are water molecules that are associated with those cations, and those cations therefore can be not just potassium, but also magnesium and calcium. And so the distance between the layers can expand because water enters there and causes expansion. Smectite, which is like montmorillonite clays, those shrinking and swelling kinds of clays, are the extreme of those where there's lots of water that can move in, but as the soil dries out, the water is expelled and the clays become closer together, and so the clay shrinks. So you have the shrinking and swelling type clays, the vermiculite type clays. Then on the far left, I'll go back to the kaolinite. This is a different arrangement where it's just a 1-to-1 type structure. You have one tetrahedron and one octahedron, and that repeats. Silica and alumina over and over again. These are clays that evolved from feldspars, lower in potassium, but then they also you find them in more weathered soils. These are the clays that predominate in the southeast of the United States, where the soils are much more weathered than they are in the Midwest. Whereas the vermiculite and the smectites, those occur in the Midwest, where you have more surface layer in between the clay layers where they can absorb water and expand and contract. And then finally, chlorite is a different example where you have a 2-to-1 type structure with an octahedral aluminum layer sandwiched in between the 2-to-1s, and then that is repeated. And that's a mineral that is subject to weathering in the soil as the weathering takes place in that environment. So these are the basic structures, the basic format that you find in soils. And as I said, the charges that are from the substitution of aluminum for silica or magnesium for aluminum exhibit on the surfaces or in between the layers. So the charges exist in between the layers, but also on the external surfaces and even on the edges a little bit where there's some fragmentation of the clay particle. And they attract cations being calcium, magnesium, potassium, sodium, ammonium, as I've shown there on the top of this figure. Because of the changes that happen in the soil environment with water moving through the soil, the temperature changes, the cations that are in solution will be associated with water. And as they're absorbed onto the clay surfaces, they bring that water with them. And that tends to cause separation of the clay particles. And so you get this sort of feathering effect on the edges where potassium can move out from between the layers and calcium, magnesium, sodium can move in, as well as ammonium. So you have this kind of ability for the soil cations to exchange in and out between the clay layers. And that's where we get our cation exchange phenomena. Again, just looking at these different structures, what I want to point out from this graphic is the amount of potassium that's associated with these different minerals. As I showed you in that first picture of the United States with the red color, that there are some soils that are just inherently high in potassium, and a lot of that potassium is absorbed between the layers where it's not available, and so you have very high total potassium content, but it's not very available. Very little of it is available to the plant or to the soil solution. Then as weathering proceeds, you get this feathering effect of the clay as zeolite is formed, and the cations can move in and out with the water. They're hydrated cations. And the wedge effect is where you get more exchange of the potassium or other cations from the clay. And you may have a high potassium content overall, but a larger portion of it becomes available as exchangeable or slowly available to the plants. And then finally, those that are highly weathered, where there's more separation between the clay layers and hydrated exchangeable cations can move in and out between the clay layers, you have a higher availability of potassium from this sort of exchange, whereas you have a lower total potassium in the soil mineralogy. In order to determine what that is, we do something called ammonia exchange to determine the cation exchange capacity. Well, in this case, and this is a typical way of performing the analysis, you saturate the soil with an ammonium solution, ammonium acetate. All that ammonium replaces all the cations that are on the exchange sites, whether on the surfaces or in between the layers, and you end up with a solution that's rich in these cations and the soil that's saturated with ammonium. And then you can determine the concentration of the cations that are in the solution, and that's how we end up with knowing how much calcium, magnesium, potassium, sodium is associated with the clay in the soil. So this cation exchange is actually an ammonium exchange for all the cations that are there. And then we just read the concentration of those cations in the extract. The relative cation exchange capacities of these different clays are here shown. The clay types, kaolinite, 3 to 15 milliequivalents per 100 grams, pretty low. Illite is in the medium range, 15 to 40. Soils are generally not only one kind of clay. You have mixtures of different kinds of clays. So you have excuse me, illite with montmorillonite. Montmorillonite has a high CEC, but it's not always the dominant form of clay in the soil. Plus, there's other minerals, other textures in the soil. So sand, generally, quartz sand particles have very low exchange capacity, but there is some clay in that soil, and so you have a CEC of 1 to 5. Whereas if you get into loam, it's higher in the 5 to 15 range, and a soil that's predominant in clay will be more in the 30 to 40 milliequivalents per 100 gram range. So you can kind of get an idea of what the CEC will be just from understanding what the texture of the soil is as well. There are resources available on our website. Feel free to download some of the same images that I use are on those resources. So feel free to access those on our AgSource website. Next, I want to talk a little bit about base saturation. What are the basic cations? What are the acidic cations? How do these ions exchange in the soil with the solution? And finally, what controls that base saturation on the CEC? The cations are listed on the left side. The ones I've already mentioned, sodium, potassium, calcium, magnesium, ammonium. These are the predominant basic cations that we talk about in soil. Interesting, though, the hydrogen is a cation, but it is the acid in the soil. And so not all cations are basic. Sodium, potassium, calcium, magnesium are basic. Ammonium acts like a base. The minor nutrients, copper, iron, they're also cations, but they are such low concentrations that we don't usually consider them. And aluminum is associated with acidic soils, so it's usually expressed in terms of acidity rather than aluminum, exchangeable aluminum. Anions are the other side, phosphate, nitrate, chloride, you're familiar with those. These are the elements that can be attracted to soil if there are any positive charges, but generally most of our clays are not, don't have that. Some organic matter exhibits positive charges, but generally these anions are mobile in the soil, and that's why you have nitrogen leaching, sulfur leaching, etc. If you look at the interaction between the clay, the solid, and the liquid in the soil, this image just shows how associations happen on the soil surfaces, humus being a representation of the organic part of the soil. And humus, actually, the organic matter has a high CEC, and it has an ability to attract a lot of cations. because it exhibits a lot of negative charges. But all of these are in equilibrium with the soil solution. So if potassium is present on the soil surface and the plant absorbs some potassium out of the soil solution, then potassium will move into the soil solution to meet the demand by the plant, and something else will take the place of potassium on the soil surface. Often that will be an acid, such as hydrogen, which being movement back and forth between the clay and the soil solution of all the cations as well as some of the anions. Phosphorus can be bound with calcium so it acts like a cation when the calcium is absorbed, but the phosphorus is just tied up with that. And that's why phosphorus actually stays in the soil over time. So there's this movement back and forth between the soil solution and the soil surfaces, the solid surfaces. Now I want to look a little bit at base saturation. So we take soil, we replace all the cations on the clay surfaces with ammonium, and then we read the concentration of the cations in that solution. We have calcium, magnesium, potassium, and sodium. And say this is a hypothetical example, we get a 75 ppm potassium, 150 magnesium, 1800 calcium, and a 30 ppm sodium. To express that in terms of cation exchange, we need to calculate the equivalent weight. So you divide those numbers by these larger numbers, which are the equivalent weight per 100 gram mass. And then you end up with the numbers that we're used to seeing in terms of CEC, the cation exchange capacity. So a 75 ppm soil in this example has a 0.19 milliequivalents per 100 grams of potassium. These numbers represent the equivalent mass of those elements per 100 grams of soil. And they add up. The base sum is 10.5 milliequivalents of cations in 100 grams of soil. Then the acidic cations, in this case, I just picked a number. I put 2.00 milliequivalents of hydrogen, which is a number that comes from the base index of the buffer pH or the buffer index evaluation. And we can calculate we can estimate the hydrogen ion content on the soil surfaces as well. Say it's 2 in this case. So the total CEC is the sum of all those cations, the basic ones and the acidic ones, and you get a 12.57 milliequivalents of CEC. Not a very high CEC, but it's in this case, that is what it is. The bottom range, so percent of CEC, this is just an expression of how much of the 12.57 is occupied by potassium, by magnesium, 9.9, by calcium, 71.6, etc. And then the very bottom line of this table is what are some of the suggested ranges for the saturations that have been found to be typical of soils that provide enough potassium, enough calcium, magnesium for a crop to grow in those soils. And so you have these ranges that they're kind of target ranges, but I'll talk more about that in just a minute. But those are expressed on a lot of reports as well. This base saturation resource is again available under our technical bulletins tab on our AgSource website, so you can look that up as well. And then find what are the factors that affect availability of potassium. One of those is how the potassium is released from the clay, but then also what tests do we use to measure that? I've talked about ammonium exchange, but there are a couple other tests. What do these tests mean in terms of the range and their availability? How do we categorize that? And then what are some considerations we can use in terms of managing potassium? I'll touch on that, and Garrett will talk more about that as he takes over after me. Again, what impacts that availability? So you've seen this slide before, but why I want to show this is that interchange between the solution and the solid is what's driving the availability of potassium and its variability. soils that have a low cation exchange capacity, you can add potassium to the soil solution and some will be absorbed, but not much. And so it's subject to movement within the soil, and it may actually be lost from leaching on a low CEC soil or a sandy soil. Where you have a higher cation exchange capacity between the clay layers because of the frayed edges from weathering processes or from a total separation of the clays from the shrinking and swelling process that happens in some soils, then you get much more exchange and retention of potassium back and forth between the solution and the solid. And what drives those things are the wetting and drying cycles, as I mentioned. Also think about temperature extremes where you have freezing that, freezing will cause water molecules to align and expand. So you get actually could be some swelling of soils from freezing process, but also freezing might draw water out of the clay because of the greater demand in the soil solution for water. And so it might actually move water the other direction. So it's not always intuitive, but these things do cause changes in the soil as you weather and as you go through the temperature and climate variation. The soil test ranges, as I mentioned, the ammonium acetate is the typical expression that I've been using in terms of the cation exchange capacity and those target ranges. Malic 3 is another extractant that we use often in the Midwest, and it typically comes up with the same number as the ammonium acetate for potassium. So those numbers, those ranges are expressed the same. You can see low being 1 to 125 ppm, adequate being 171 to 220, and anything over 221 being high or very high. In Wisconsin, a different extraction process is used. They use a Bray to measure phosphorus, but they also read the potassium in that same extract solution. And because it's not rich in ammonium, it doesn't extract as much. And so you get lower numbers. And these are expressed here as well. The target or the adequate concentration being between 90 and 110. And then there's another method of analysis that used to be very popular in Iowa. It's still used in Iowa and is available in the AgSource lab in Iowa. And this is an extraction where you don't dry the soil, but you leave the soil in a moist condition when it comes out of the field, and then extract it with, in our case, malic, to get the potassium that's associated with those moist clay particles. And the reason behind this is because it's been found on some soils, particularly those that have a lot of shrink and swell capacity, that drying the soil tends to elevate the potassium content that you test. It drives more potassium. Drying the soil tends to drive more potassium into solution, and so you have a higher value. So where you get 100 to 150 as the target range for some soils with the moist method, generally 170 to 220 is the associated range that you would see in soils that are run, or analysis that's run on a dried soil for the same kind of soil. This is a illustration of how that moist reaction takes place. On the left side is a plot of soil test values at the bottom and relative corn yield on the vertical axis. And so each one of these dots is a representation of the yield for a given soil test value at a given plot or a given soil for a given year. And this is a summary based on research done in Iowa over a number of years to come up with a graph like this, where you can see that as they approach 100% yield, the graph tends to move towards the right. And so you see the optimum level is targeted around 150. This is an old graph, so it's a little bit lower. This is the old ranges. Iowa has since updated their ranges, but the range was between 120 and 180. And you can see that is the optimum range. And the bulk of the samples or the plots that yielded from 90 and above, 90% yield and above, fall within that range or to the right of that range. If you look at the moist soil K on the right, it's a very different distribution. And what really has happened is these are the same plots, but the same soils run with a moist extraction, and everything got shifted to the left. That's because the moist extraction extracts less. But what really happened, look at the black dots. The gray dots didn't shift that much, but the black dots all scrunched over to the left. And so they're lined up right along that axis of right above 50 ppm. And this is an illustration of how for poorly drained soils, that's what the black dots, they come from those soils that have the shrinking and swelling capacity. For poorly drained soils, this method is better at predicting what is the target range. So the M, being the target range, is more clearly visible here because it's left of, I mean, it's right of the very low where all those vertical line of all those results are. And so that's why that is favored for some soils, but it's not universally applicable, and it is not, I wouldn't, it is offered, but it's not something that is easily done in the laboratory. And so you end up paying a premium to get this test done by the lab as well. What do those terms mean in terms of relative yield? Well, it's all about probability of seeing a response to potassium fertilizer. If it's very low or low, chances are you will see a response when you apply potash to your field. Anything above the optimum level, below the optimum level, you'll see at least a 50% or higher probability of getting a response. When it's in that optimum range, which by the dry method is 70 to 220 ppmk, 1 out of 4 years you might see a response, but the other 3 years you probably won't. And so that's why recommendations are to maintain it at that level. And some people will apply a little bit more just to have a bit of insurance, but the chances 3 out of 4 years you're not going to see a response to any application. And then if it's above the optimum level, you will not see a response to applied potash fertilizer. So looking quickly again, remember this chart. This is the hypothetical soil, 75 ppm potassium. Just keep that number in mind. And this number at the bottom, the 2 to 7% saturation. With those numbers in mind, on the left side of this figure is the concentration in the soil that would represent the percent saturation at the top. So for a 5 CEC soil, right at the top of that chart, if you go across the top, if it were 3% saturated, that means it should test at 58.5% or 58.5 ppm potash. 78 ppm potassium would give you about 4% saturation. If you go down to the line that's 15 milliequivalents, it would take your target is 175 ppm. That's the optimum level. And at that optimum level, you're about 3% saturated. You're saturating 3% of the CEC with potassium. At the higher CECs, 30, even at 175 parts per million potassium on a 30 CEC soil, that is only occupying 1.5% of the CEC. So you see how that line diagonally goes across. And the higher the CEC, the more potassium it takes to meet that high saturation equivalent. And that's what the chart on the right is showing. To meet those equivalents, to change that soil that was 75 parts per million, to boost it up to 175 ppm, it's going to take you 500, well, look at 25 CEC soil. It's going to take you 570 pounds of potash to raise the soil test level from 75 ppm to 175 ppm. That's a huge application. And so you don't want to do that in 1 year. You do want to build to that for a soil that has a high CEC, but that's something you want to do over time. But notice that to the right of that blue diagonal line, those numbers get extremely high, and there's no financial incentive that applies in trying to change a soil from a 2% potassium saturation to a 4% saturation when your CEC is 20. it just triples the amount of potassium that you have to apply. So this is a graph showing actual values, soil samples that were run in the Ellsworth laboratory. The dark blue line are the parts per million potassium in about 1,000 samples, and the light blue values are those equivalent cation exchange percent saturation of the cation exchange capacity of the CEC. So you can see the horizontal line represents 2% of CEC, and the vertical line represents about 175 ppm potassium. This little blue circle are samples that are higher than 175 ppm, but they're lower than 2% saturation. Not many samples fall in that category, and you're meeting the needs of the crop by applying enough to meet that sufficiency level, but you're probably not saturating the soil. You have a very low saturation, but yet it's enough to meet the needs of the soil. The other scenario is where you're not meeting the sufficiency level, but you are meeting that percent of saturation. And here, I think this is more of a concern where the crop is potentially deficient in potassium because it's just not having an adequate supply over time. And yet the saturation percentage is high because probably the soil has a low CEC. And so on those soils, the chances are you have to apply smaller amounts of potassium over time to maintain the availability of potash as it goes forward. So with that, just a reminder that there are other bulletins available that we'll talk about this on the website under technical bulletins. And I believe it's Garrett's turn. So I will turn it over to Garrett.
All right. Well, thank you for that, Jim. And just sitting here thinking about how all of our presentation kind of overlaps. Everything is mutually connected. So when Jim's talking about all of the clay, how the potassium is interacting in the clay, and then how we make recommendations based on that, how it all kind of goes together and it comes full circle. So when we're looking at this chart here, this is corn and soybean yields in Iowa. You can see the region here in the top right corner. You got the Northeast region, the North region, and so on. But we just want to look at the mean here. So when we look at the mean of all of this soil data over the last 16 years, you can see how the soil test ranges are in the black triangles, and they're very up and down. So as Jim kind of talked about, we see that change over time, mainly because you're talking dry soil conditions. Maybe some of these are, maybe some of these samples are taken in the fall versus the spring, things of that nature, where you can see, take this last year, for instance, we had a very wet spring, but then when we got to the fall time, it really dried up. And those things like that can greatly affect that potassium value. So when we start getting into recommendations, we're looking at building the fertility to a target level. I just wanted to emphasize for phosphorus, we're using 18 pounds per part per million changed. For potassium, we're using 8 pounds per part per million. And then just how, when we build, it's going to be over a few years. So how many years is it going to take you to build to that level? And then what's your crop removal? We want to obviously reduce excessively high fertility, especially on low CEC soils. So I'm going to get a lot into how does the CEC affect what our fertility recommendation is. So we'll get into that here. There we go. So calculating removal rates of potassium. So I just used the 250 bushel yield goal with 0.3 pounds of potassium removed per bushel. That gives us 75 pounds of potassium removed in that crop for the grain portion of that. Then when we look at it on a soil test side, how do we convert that pounds of K that we removed into, this is how much I can expect my part per million to move on my soil test. So when we divide that by 8 pounds of K2O per part per million, we're looking at about 10 pounds of potassium removed with that 250 bushel yield goal. On the soybean side, obviously our removal is a little bit more. You're looking at around 1.4 pounds of K removed. And this is what I would emphasize on this is 60 bushel soybeans, especially in an irrigated scenario or more of a what quote unquote normal year in Iowa where they're getting adequate rain. You know, that should be very doable with those varieties that we have out now. So you're looking at 83 pounds of potassium removed, or right about at that same 10 part per million K removed per year. So then when we're thinking about, I want to say it was about 2016, 2015-ish. There was a big push in Nebraska for corn stover removal, and people were going to come in and buy your stover, and they were going to make it into pellets for cattle and make that feed. What I feel like a lot of people missed was how much phosphorus and potassium you're actually going to lose by doing that. So I just went ahead and ran the numbers on a 200 bushel per acre crop. You're getting about 4 3/4 tons of stover. So you're looking at about another 10 part per million removed. So, taking you back to the last slide, you had 75 pounds of removal on the last slide, or sorry, 10 pounds of removal on the last slide, 10 additional pounds of removal on this side. So you're looking at a total of 20 part per million change. You really got to start thinking about how is that going to affect your next crop, and what is the price of fertilizer doing? And is it really worth removing all of those nutrients? Now, on the flip side of that, if you get adequate rain early on, you can see some of that potassium move back into the soil, as it's somewhat of a quick process with adequate rain. Most of that potassium gets solubilized in water and moved back, but you're still removing a fair amount of it. Oops. So here we're looking at kind of all-encompassing of what Jim just talked about in his whole presentation. Base saturation recommendations, they want you to be between 2 and 7% of the CEC for potassium. The sufficiency level is 170 to 220 part per million on your ammonium acetate extraction. So which one of these is correct? And that's something that we're going to explore here. The short answer is, in any scenario, one of them can be correct, the other one can be correct, or they can both be correct. So let's get into a little bit of that here. So next we're looking at the CEC, as Jim has already discussed in detail. So I'll go pretty quick here. 1 to 8 CEC, you're looking at a sand versus 29. So you'd be looking at less clay in that sample. 29 to 40, you're looking at a lot more clay, a lot more holding capacity, probably a lot more potassium in that soil. So I'm a big picture guy, and it just helps me see it helps you visualize what's going on in the soil versus just sitting here and talking about it. So what is the difference between the part per million and the base saturation? So on the left, you have a high CEC, and on the right, you have a low CEC, which would be a sand. So we can see the amount of exchange sites on the clay, all the little negative dashes, are spots where all of your cations can attach to. So we've already covered that quite a bit. So we can see that on that clay particle, there's a lot more area for those cations to attach. First, on the sand, there's not near as many particle or exchange sites for that potassium and magnesium. So the CEC is what's occupied by those ions. The part per million is the concentration of the potassium in the soil. And generally they're inversely related. So as your part per million goes up, your base saturation goes down, and the opposite. So as your part per million goes up, you're usually getting into more of those clay type soils. As your part per million goes down, generally you're getting into more of those sandy loam or sandy soils. Let's go to the next slide here. So then just taking that that thought process of how we apply potassium and based on our CEC. So we can see here that comparing our potassium to our nitrogen, it's going to move down through the profile where the phosphorus is going to generally stay right where it's at. So you see the colored here, the little colors are blue, red, and purple. So those are where the initial placement of the fertilizer was. That would be day 1. And then on day 17, the IPNI measured how much that fertilizer had moved in the soil. And you can see that the potassium is going to move down through the soil. So we think of things like low CEC soils. You're going to see more of this movement downward, like in the picture on the right. A higher CEC soil where you're not going to see quite as much movement downward, because you have that more of those negative charging exchange sites that are holding that potassium up in the soil. So the higher the CEC, the less movement you'll see. The lower the CEC, the more movement you'll see. So now I wanted to look at just some trends over the years. So this is the last 5 years of soil data out of our Lincoln lab. Some of this has to take into account where our labs are located and what kind of soils are coming into the lab. So Lincoln is going to see a lot of Nebraska, Kansas, South Dakota, and so they're generally going to have higher part per millions of potassium just in their parent material. So you can see in 2019 we were sitting at one of our higher readings of 252 part per million versus 2020 was a very low year. What I would say about 2020 is it was one of our highest throughput of samples in the last 5 years. So some of that could be just due to the amount of excess samples that year saw. The other thing I would say is in Nebraska, in general, we have higher potassium values in our soils just due to parent materials. So over the last, say, 20 years, we've seen that those values are coming down from, say, 400 and 350 part per million down to this 250 part per million mark. Some of that is due to increased yields and things of that nature, but also we can see that we're coming back up on the bottom end of this. 2024, there's not quite as many samples. Our average so far this year is about 305 part per million. But these farmers have seen this trend of decreasing potassium values over the years, where they've mainly been focused on phosphorus in Nebraska. And so now they're really starting to say, hey, I don't want to see these values end up down in the the 150s, the 200s, to where I'm going to have to apply every year. So we're going to apply, say, a maintenance rate, or just apply our removal from what we removed in the grain. So our next slide here, this is just breaking that same data that we had before out into the bins that Jim had shown earlier. So of the samples that we ran from 2019 to 2023, on the left is very low and on the right is in the very high category. So you're looking at very high being over 270 part per million. So we see that trend a little bit more in that some of those guys that maybe had adequate part per million values are now looking at, hey, I want to go and maintain this level, or I want to apply the removal rate that I took off the field this year. so that we're not seeing those values continue to decline, especially in the market. I know early on that potassium was going to be relatively cheap compared to your other inputs. I heard one farmer was talking, it was the cheapest they'd seen potassium since 2010. So, you know, some of that stuff comes into account when we're seeing these trends of lower potassium values. So this would be our Iowa location. Iowa in general is going to see their parent material is going to have a lot lower values of potassium, and so you're going to see a lot tighter correlations because they're over in Iowa. There's a lot more people that are applying. I would say, if not every year, they're applying every other year, because they're kind of on the forefront of what's happening in Nebraska and seeing that lower part per million value, as well as seeing their yields continue to increase. Minus maybe the last couple of years with some of the drier weather that we've had. So same thing, broke down by low, or very low, low, adequate, high, and very high. And we see some of the same trends in 2024 so far. We see that very low trend, or that very low category is a little bit smaller, and some of that adequate or high values are being transitioned into that very high because they're trying to manage that potassium drawdown in the soil. So I would say that Nebraska and Iowa, as far as the trends go, are pretty similar. And then we look at Wisconsin. So as Jim alluded to, this is a different extraction type. So they're using a brake hay extractant. And so the numbers are a lot lower. But still, we're seeing that the lowest values were in 2019, and we're gradually increasing those. And just looking at the trends on this graph, you can see that in October we kind of go up, and then the values start to decline through November and December. And some of that could be due to just the drying. Some of it will have to do with less sample volume, but then also just getting dry in the fall. And then again, we're looking at the categories. So very similar here with the other two. You're seeing your very low category shrink just a little bit, and the very high category just expand just a little bit. So very intuitive stuff there. So now we're looking at, there we go. Now getting into looking at tissue samples. So we've addressed that when it comes to applying fertilizer for potassium, you're really going to be using that CEC and the base saturation. If you have a low base saturation, maybe you want to look at more spoon feeding type applications. If you have a high CEC and you're not going to leach very much of that fertilizer, you can look at larger applications, and maybe spreading those applications out over the years. But when we look at tissue samples, there's multiple things that we want to look at. So you have to take into account your growth stage. The biggest growth stage in corn is that V6 to R1 time when we're thinking about things like the cell elongation. So we're thinking about times that we have green snap. We're applying nitrogen fertilizer that we're expecting that corn to grow in a fast manner, and we want to have the potassium out there that's going to be able to make those cell walls rigid, and so that corn doesn't just fall over. With soybeans, we're thinking about flowering into grain fill, pod fill. So you're looking at about 80 days after planting, and we're really focused on that pod fill time frame. And so back to what I was talking about earlier, the CEC is the best way to address a tissue deficiency for the soil type. So, based on your tissue sample, you might say, hey, I need a foliar out there now. But in the larger scheme of things, that foliar is just going to be more of a band-aid to a larger soil problem. And so addressing the soil problem based on your CEC is going to be the best approach. So when we have a low CEC soil, we don't want to apply large amounts of dry fertilizer at one time. We want to use the, and not even necessarily the spoon feed method, but say you put out 50 to 150 pounds, then you're just, you know that you have some that's going to be in the soil solution for the next crop, versus going out there with, say, like a 4-year rec and then losing that all to leaching. In the low CEC soils, you're also going to have to use your foliar fertilizers to address in-season problems more. And that's generally due to, say, you couldn't apply enough of the dry fertilizer to get all the way through the year. So you're looking at that, taking some of that stress off the crop in season. Versus if you have a high CEC soil, you can apply more at one time, and you won't lose as much to leaching. So here's our in-season soil tissue report. So this would be three tissue sampling dates. So on the same field. So generally these would be in the same. I see we have one here that says 2023, but generally that would be all the same year. So, say you wanted to do beginning, middle, and end, or however you want to do it, but we can plot them versus time and then show you this is how you're trending versus what the uptake might be and things of that nature. So this has been really helpful in seeing that in-season tissue, how we're managing that throughout the season. So lastly, the deficiency symptoms. We can wait to see the deficiency, or we can try to take tissue samples and apply before we have a deficiency, so we're not seeing some of that yield loss. In general, corn tissue, you want to see over 2%. And then in soybeans, you're trying to stay closer to 1.7% potassium. And I thought this was a really interesting kind of study that Iowa State did in the picture in the bottom left, where when you have that potassium deficiency, it can really exacerbate some of your disease symptoms, and they can look the same. So it might be a disease, it might be a potassium deficiency, but in some cases it's both, and it looks a lot worse. So just taking that into account, and maybe that some tissue samples throughout the year could have helped with the senescence of those leaves based on what you're seeing in season. And then lastly, the corn plant calcium, magnesium, and potassium relationship. If you're 10 to 1 or less, it's satisfactory. But if you get over that 14 to 1, you can see some restriction in growth. But yeah, so that's, now we have our, oops, hit the wrong button. So for all of this, any tissue questions you have, any soil questions you have, we have really good resources online. If you just go to agsource.com, you can navigate to the agronomy technical bulletins, and they come in really handy, especially when you're trying to decide, what kind of fertilizing should I be doing? Should I be using foliars? What's my tissue sample mean? Those kind of questions, it can answer a lot of those. So here are our lab locations. So lastly, here is the CCA QR code. Feel free to take a picture of that. We'll leave that up.
Thank you both. I know we are over on time. We did have a few questions come in, so I want to try and address those super quick. So the first one came in, Jim, while you were presenting. CEC, you have calculated, is a sum of K, magnesium, calcium, sodium, and hydrogen plus. Have you considered whether the addition of micronutrient cations should also be included to calculate CEC?
Generally, they're not included, sorry, just because the concentrations are so low. and they're micronutrients, and there's not a very high concentration in the soil, and so their impact on the CEC is minor compared to calcium and magnesium, which are dominant. And those, so they could be, I guess, if you had a high manganese soil or high iron content, but generally we don't think about it, and we don't use them in that calculation.
Okay, next question. Would using more potassium as a granular starter make more potassium available for plant use in clay soils?
So this question is interesting. I haven't seen granular starter, with a lot of potassium. What I would say is, just in regards to the more potassium available for plant use, the answer to that would be yes. Where I would get a little weary would be putting it in, I don't know exactly, if you're putting it in furrow or side dressing it or exactly, but I would just be concerned with, injuring the germination. So you'd certainly want to test that before doing anything at scale.
Thank you so much, everyone, for your time today. We greatly appreciate it. If you have any questions or want to get a hold of any of our labs or reach out to Jim or Garrett, please go to the Contact Us page at agsource.com. We appreciate everyone's time today. Thank you, Jim. Thank you, Garrett, for your expertise. It's greatly appreciated. We hope everyone has a great day.
Thank you.